Welcome back. So in the past couple sections, we've been working with multivariable functions. That is, functions with more than one input. Well, as this class is Calculus 3, we need to do some calculus with these functions. And so the easiest thing to start with is derivatives. So how do we take a derivative of a function with more than one variable? So let's look back at a function of a single variable, just f of x. How do we find its derivative? Remember, its derivative we call, let's do a little arrow here, so df dx, right? Or we might have just called this f prime, right? How did we define this derivative? Well, you might remember what we did is we take a limit as h goes to 0 of f of x plus h minus f of x, all of this over h, right? So what it's sort of doing is the instantaneous rate of change, or the slope of the tangent line, right? That's what this was. Okay, well, for multivariables, for more than one variable, well, we can't, there's more than one way to pull off this kind of quotient. And for that reason, we're going to be doing things that we call partial derivatives, right? We're going to only take derivatives of the function with respect to one variable at a time. So, you know, it's a piece of it, right? So let's look at a function f of xy, right? Now we have this two-variable function. And there's two ways we can write down sort of this sort of thing here, right? So let's kind of skip these two parts real quick and come over here. We can still do limit as h goes to 0. Let's start with x this time, right? So we can do f of x plus h, comma y, minus f of xy, all this over h. We can still write this thing down. It completely ignores anything that's happening to the y variable, but it still does the rate of change in x. So this is what we'll call the partial derivative with respect to x. We have a couple different ways we write this down. One way is the subscript, f subscript x. This is still a function of x and y. Right? That's one notation we have. And another one to match this, it looks basically the same, but we're going to write the d a little bit differently. And that's going to signify that it's a partial derivative versus being like a total derivative, so to speak. Right? And that looks like this, sort of a curly d. Right? And if you like, you know, up here you could also have of x. In here you can write of x and y if you like. Usually when we write it as the quotient like this, we can leave off this of xy pretty easily. Over here I think it's a little more important to keep it because this looks more like a function. Just like up here, you usually don't write f prime, but you write f prime of x. All right, so that was the partial derivative with respect to x. So here, let's write that down. Partial derivative with respect to x. Right, and then we can do the same thing, but for the y variable now. So df dy, and I'm going to leave off the of xy this time. F is the, so the other notation is f sub y, right? And take a second, guess what you think the partial derivative with respect to y should look like as a difference quotient. Okay? So you should see that that's just limit as h goes to 0 of f of x comma y plus h minus f of xy, all of this over h. Right? And that's the partial derivative. So this is partial derivative with respect to y. Right? So you might imagine, of course, it would be pretty easy if you had a function that was, say, f of x, y, and z. You could do 3 partial derivatives with respect to x, with respect to y, and then with respect to z. These first two, the definition looks exactly the same, except now there's a comma z at the end there. And, well, when you take the partial derivative with respect to z, you just have f of x comma y comma z plus h minus f of x, y, z divided by h, limit as h goes to 0. Right? So what do these numbers represent? Well, I mean, we can say it's the rate of change of this function in the x direction, in the y direction, or the z direction, or if you like, in the I direction, the j direction, and the k direction, respectively. Or you can also think of it as the slope of a certain tangent line. So if you, let's stick with just this case here, and let's graph an equation like z equals f of x, y. That'll give us a surface, and then we can see that these derivatives are just the slopes of certain sort of paths on that surface. So in the next video, we'll have a Mathematica demonstration of this concept. We'll graph a surface and then look at the tangent line, look at these curves and then look at their tangent lines and the slope of them.